you are losing a lot of value if you can't make it. There's an enormous return on investment for any company that's paying a developer a reasonable developer wage and sends their developers here. I can't tell you how big of a mistake it is not to send someone to CppCon.
Okay, in the presentation, please interrupt me to ask questions or even make a comment if you feel like it, okay? I have plenty of things to tell you about. However, you don't have to fully understand all of the things that I'm going to be talking about because the amount of material builds towards the idea that I want to present to you, and they are just small contributors that aggregate into a fuller understanding. Okay, who am I? For those who don't know me, I am a tech lead in C++ at the team of camera platform of Snap. Snap makes the public application Snapchat. I have had several presentations and conferences like this. I carry experience from working in financial technologies, in particular automated trading, which very low latencies and very reliable software are truly important. This work is about the benefits of data orientation techniques and an attempt to make them practical so that we can start using them. Okay, and the most important assumption that I'm going to make today is that most of the audience is very familiar with object orientation, but almost not familiar at all with data orientation. If I go over things that you already know, that is the reason. Okay, why data orientation? The simple answer is performance. We leave quite a lot of performance on the table by programming the classical C++ way, including object orientation. We will see momentarily that object-oriented code is very removed from the real execution hardware where we run our code. And that very big gap means that we cannot use the particulars, the details of the executing platform that our software is running on top most of the time. So we have been programming in a way in which object orientation attempts to relieve the programmer from the details of the implementations, and the execution platforms are just another detail, and that has served us really, really well. So we want for the programmers that are going to be using our code to be able to continue to not have to concern themselves with the details, but at the same time, we don't want to prevent ourselves from being able to access as much detail as we want from the executing platform that we're going to be running on, okay? The inefficiencies are very real and very well documented by the people that have gone over them, okay? In the interest of focusing on making this practical for you, I'm not going to be persuading you of the big benefits, except to mention the direction in which we can get benefits, because we had to focus on making this thing practical. You will see that I have plenty of material, and that'll be the reason for why I had to make cuts. Okay. There are many places where you can go find data orientation benefits and see excellent benchmarks and so on. Now, although you can do that and get really good benchmarks and so on, I will tell you momentarily that there is a problem because the people that do data orientation don't articulate this very well, okay? So, we'll talk about more in a moment. Okay. So what is the plan? Well, we had to go from the orthodox way to do software, which is using things like familiarity of encapsulation and things like that, and do things that are very unfamiliar to us, okay? The thing is that when you are doing the orthodox thing, there's like a one prescribed best practice way of doing it. But if you go into the heterodox, there are plenty of opportunities to do it in multiple and very different ways that are just trade-offs between different things, so it's not clear that one is better than the other, okay? For that reason, I am going to focus almost exclusively on the reasoning process to arrive to practical solutions to how to take advantage of data orientation as opposed to sell to you the solution that I have been working on, okay? The consequence of what I just said is that we're gonna be de-emphasizing looking at code, because otherwise we're gonna get confused. We're gonna be talking about unfamiliar techniques that are applied to get unfamiliar results too. So we have to use our time into explaining better where we're going so that we really understand where we're going rather than a particular solution in the form of code that gets us there, okay? And to be honest, in the process of preparing for this and developing my own work, there are many questions that I have not gotten to an answer that I feel confident or satisfied. It's not an obstacle, but it is like a not ready. So I don't want to confuse people because of that reason, okay? Well, what is data orientation? This is very loosely articulated in presentation books and blogs. And that's fine because the people who have done data orientation, very obviously, if you check, are practitioners, and it's perfectly fine that they are not into articulating or theorizing what they're doing. The problem is that they contradict sometimes, okay? And for that reason, I think that the focus on what data orientation is should come from a keynote presentation on 2014 by Mike Acton. It was a very popular presentation, and a lot of people saw a lot of value in it. And I really like it because it is extraordinarily critical of C++, and then I come and I use techniques that he rejects to achieve the same results that he likes. So I am going to, in a way, argue the case for C++, which is something that has not been addressed by the community as far as I can tell, okay? Because his presentation is extraordinarily critical, and nobody came and said, no, wait a minute, you can do this and that and the other. Okay, obviously, I'm not fully convinced of the tenets of what they say, okay? Again, the value of what they have said is there, undeniably. But there are some opinions that I can simply not go there. Let me give you one example. At the end of his presentation, Mike Acton said that C++ has a bad element to it, which is a culture that thinks that ignoring the real problem is a good thing. So he thinks that we C++ programmers don't attempt to solve the real problems. We do something else. He quotes this asinine, completely obtuse quotation from some rando there that goes like this: design patterns are a spoon-feed material for brainless programmers incapable of independent thought, who will be resolved to producing code as mediocre as design patterns they use to create it. He quoted this, okay? So that attitude, of course, I cannot go there, and the reasoning process that led them arrive to these opinions, very quickly they leave me, they drop me off. Okay, now, what is the focus of what we do? Abstraction and modeling, okay? Because we are trying to put the real world with its complexities into software. We concentrate about the performance a little bit later, not from the beginning, okay? And we are successful. That's why our way of doing things, which is the orthodox way, is far more popular, okay? And I mean not just C++ programmers, but programmers of many other languages too. Okay, we achieve facilitating the evolution of code to new applications with techniques such as design patterns. And if you want to know more about design patterns, please visit the work of Klaus Egelberger. I think that his work is excellent. And I don't say this because he's my friend, but because actually I think that I got really interested in becoming his friend because his work is so amazing to me. And you will see that there is no disconnect between attempting to achieve very great performance with things like what Klaus has been talking about, design patterns, for example. Okay, what is the fundamental tenet? Data orientation is to give primacy to the data, to the processes on the data, the computations that you're going to be executing on data. That contrasts to our normal attitude, which is, for example, the classes are black boxes, and we don't even care what's inside. We should not care. We care about only the interfaces, right? We have articulated this in many different ways. There's the principle of least knowledge, the law of Demeter, and so on. I am just going to summarize using one word. It's not perfect for it, but I need only one word, which is encapsulation. Now, data orientation, I will attempt to use simple data types to attempt to get simpler and more performant code. And we had to capture the opportunity to map real computations to real hardware directly. Okay, the people that do data orientation, as I said, is hostile. I'm going to skip this slide. My slides are always very heavy, so they are meant for people to revisit the topic as opposed to read them in the presentation. Point is that data orientation, people probably won't tell us how to do tricks in C++ to accomplish data orientation. So it has got to be someone who is not a data-oriented person, but who knows C++, who attempts to do that, and that's me. So, okay. There's tension between principles, okay? Our orthodox way of doing things and mapping directly to the hardware. The reason must prevail, says Mike Acton. And for the rest of the talk, we had to take into account something very important, which is my favorite engineering dictum. The difference between theory and practice is far larger in practice than in theory, okay? Because we have this abstract model of computation and computing devices, and that's what gets us into the trouble that we leave massive amounts of performance on the table. Okay, we are gonna be reasoning from first principles, so we always know why we do what we do in terms of the choices. Okay, some problems with object orientation. We do not concern ourselves with implementation details, therefore, inherently, we do not use opportunities of concerning with those details, right? Now, let me give you a very simple example. In object orientation, it is prescribed that they are black boxes, and therefore, the class is going to maintain the invariance of the object. And this very naturally leads to memory layouts in which several things are put together, joining in memory, and that's the normal memory layout that we have been using all the time. The problem is that that is heterogeneous data, that it is impossible to map to real hardware for truly efficient computation, okay? And one example is you have, for example, a data type that only takes 16 bytes. It's a small data type, and you only use one of the members of that data type because the others are there. Every time that you go to memory to fetch that value, that field from a particular object, you're bringing in the whole cache line, which is 64 bytes, okay? So you are having an inefficiency in terms of bandwidth right there of 1 to 16. And that inefficiency of bandwidth is exactly the same with regards to the utilization of the cache. So effectively, we are slashing by a factor of 16 the sizes of our caches. Massive amounts of performance left there. And we are doing things that are inherently efficient. We leave a space for optional fields, like, for example, something that can be a null pointer, which has optionality to it. Well, it has to be there because who knows who's going to have it, right? If it would be something, a different scenario in which we know for a fact that that optionality is going to be present in the actual object very, very statistically seldom, then we could implement some other representation in which we are not wasting that memory for all of our computations. Okay, alignment padding. And then the other problem that when you have subclasses, especially if you use runtime-polymorphism, the subclasses make the layout unpredictable, so you have to indirect, instead of dealing directly with the object, you're using a reference or a pointer to something typically allocated on the stack. So, okay. What would be the benefits of breaking this way of doing things? Well, this problem gets worse because we have now GPUs that only work well with data that is local to them and data that is homogeneous. We have other types of non-uniform memory architectures, vector units, weird processor instructions. There are opportunities that are completely untapped. What is the solution for this dichotomy? Number one, like I said a few minutes ago, the user programmers should continue to not concern themselves with details, but we need to have access to the details. So this is a dichotomy, is apparently an unresolvable conflict, but to bring the point home, I'm just going to go with an example from my Acton 2, which is every time that we implement maps, the storage for that map is going to be on a standard pair of the key and the value, right? However, ask yourselves, what is more often? To use both the key and the value, or to use the key far more often than the key and the value? So every time that we're using the key, we had to bring into memory, from memory to the cache, or from the level 3 to 2 to 1 to register, the whole value too, okay? That's an inefficiency. And to be honest, I was made aware by it just reviewing his presentation for this presentation. I made that mistake very recently in something that I attempted to be the best performing hash map that I could make. Well, I think that the conclusion that we have to arrive is we cannot use normal struct layouts to represent states. So what we're going to be using then? I have this very simple example. Let's say you have a stock keeping unit. It is composed of the fields that you see there. And just a comment for you to keep in mind, the specials of the SKU are going to be very rare. Very few SKUs are going to have specials, okay? One reasonable way to represent this, I think, is in this way. We're going to have something that I call state that is going to contain arrays in which you put the fields, each of the fields of the original object, which is the SKU, and to mediate to that collection of arrays, a handle class. And to refer to the individual fields that corresponded to the original class, you have an index. And you index into those arrays. Now, I was telling you that the specials are very rare in this particular scenario. Then maybe it is not as efficient to represent that specials fields as an array themselves, but we can use the fact that there are going to be a few of them to use a normally more expensive data structure, which is a map, but that would work better if the number of elements is smaller. And for the same reason, the Boolean of made in place can be, comes from a Boolean, and we can represent it as a set. And you know, right there we have a compression of 8 bits to 1, okay? In the worst of cases. So we're ahead. The handle has accessors that does the dereferencing on the things that contain their states. And look at this. You have the same syntax, and this is important from the perspective of how we're going to make this automatic. The same syntax of bracket dereferencing, and that'll work for the efficient map and efficient set. Okay. This is the representation, the architectural transformation that we have done, okay? I hope that this is clear. Questions so far? If you got to understand this, then the rest is going to be just benefit for you. All right. So let us capitulate on how we can do an equivalent representation for the state of the objects. Okay, we use arrays with sets and maps for optional fields or for support for subtyping, and I will tell you about subtyping in a moment. This is commonly called scattering or parallel arrays. I don't like any of the two terms, so I'm going to refer to it as columnar representation because I think that the people in databases that have studied about when to represent a database table has rows, collections of rows, as opposed to representing a table has collection of columns. I think that they have an advantage in terms of how clearly they have articulated why they do things, okay? So I'm going to use columnar. But commonly this is referred to as scattering or parallel arrays. Okay, and just a note of a mental note. What we're doing with the handles are just the strong integers. Yeah. By the way, managing the addition and deletion of entities is far easier than allocation and the allocation, okay? If you don't have to program the allocator, then you don't know how much of work that represents. But in this particular example, the allocation and the allocation is to just determine whether an available slot is used or not. Managing that is far easier. Plus, there is a big difference that we're going to refer to at the end of the presentation, which is with allocations, the addresses of the objects are unpredictable. With using indices, instead, you control the arrays that they refer to, and you can achieve predictability of where the object is going to be allocated, meaning what is the index that it's going to receive. Then you have more performance. Okay. Now let's talk about runtime polymorphism and subtyping. Fortunately, I don't have time to talk to you more about this subject that is truly dear to me. But we should not use the word of subclass or inheritance to refer to subtyping, okay? What we want is substitutability, meaning that if you want to do whatever you do with a shape, you can substitute in a circle, a square, a triangle, all right? That is substitutability, what we have done with polymorphism all the time, okay? Now, polymorphism requires something that is going to activate the true behavior of the actual type of the object at runtime, and I call that the type switch. In C++, the only type switch that you have is the virtual table pointer. But the problem is that is an implicit member. You don't have any control over it, and that is so problematic that probably so subtyping. I was telling you earlier that the memory layouts from the perspective of the base class, if you want to use a shape, and you're going to have a circle or a triangle or so on, you cannot predict what is the memory layout of the actual object in memory. All that you can do is to use an indirection. And then you turn on allocations, and allocation means locking the mutex for the heap, and running the allocation itself is complicated and expensive. This breaks local reasoning. You have to concern yourself with lifetimes, ownership. You have the incentive to share the state, because if it is expensive to do an allocation, then you want to minimize those allocations, and perhaps you're going to change the design so that you are optimizing, but by sharing a state, and that has its own host of problems. So this compounds exponentially with the level of nesting of something that is polymorphic, that has a member that is polymorphic, that has a member that is polymorphic, in my opinion, okay? The conclusion is that we cannot use inheritance and virtual. What are we going to do instead? Well, you know, from the perspective of activating the right behavior, that's simple, okay? Because that is just, we can put in as a member the equivalent of a virtual table pointer. that has the virtual table will have the right function pointers that will activate the behavior for the particular object that you're having. So it's not a problem. Just we have to make it explicit. Another way to implement subtyping is you can think of it as the fields of a subtype are, from the perspective of the supertype, optional. You see? So you can use whatever you use for optionality on the base class, on the base type, for the support of the state of the subtypes. That's another choice that we have. Finally, you can also recur of doing the same transformation of making the scattering or the columnar transformation of the extra fields that a subtype present to you. Now, what do we do with the handles of subtypes? Like, for example, what would be the handle of a circle if we had the handle of a shape? I think that this is something that fits the bill just fine. We have a handle for shape, which is the handle for the base class. We just make it so that the handle for a subclass is a derived class of the superclass handle. And we are going to have to put there, in the interest of invoking that a particular behavior as fast as possible, only one indirection, so we're going to put it through the mechanism of scattering. We could, but we're not going to.
Is circle final here?
No, it doesn't have to be final.
Because otherwise we could end up with multiple V tables, right?
Yes, we're going to have multiple V tables. The thing is that the derived classes would have either, because again, when you're going to implement the subtype of a subtype, you again have the choices of implementing it as optionality on the base class or base type, or using the virtual table pointer, okay? So there are many ways to skin these things, and this is one in which you can do them, okay?
Could you repeat the question?
Yes, the question was whether, in this case, the circle class had to be final.
Hey, with the columnar representation of subtyping, it sounds like that can only be used if you already know all of the subtypes. So if you're writing a library and something creates a new subtype, then you would need another map of values.
Well, okay. The question is whether if you have subtypes represented in a scattered way or columnar way, you need to know the whole set of possible subtypes to make this implementation. And my answer is only in the case of representing as optionality on the base class, because you are putting optional things in the base, in the supertype, to support the subtypes, right? But if you don't do that, if you use just the option of the virtual table, it is exactly the same as in normal inheritance. The virtual table takes care of being able to extend the base class without the base class knowing that it's going to be extended. Thank you for the question. A third problem that we have in orthodox programming is that we're designing it for generality rather than the frequent uses, okay? And I think that this has a reason. The work that we do at the beginning is top-down. We try to model reality so that we can be sure that all of the operations that we want are going to be supported. So we are, in effect, designing for generality. The data orientation people always tell you it is better to start from the bottom up and see, okay, this is what I want to run fast, so I'm going to make my system to have this thing run fast, and then they add functionality on top of it. Problem is that they very quickly run into a wall of complexity that they cannot deal with, in the same way that going top-down, we get to a point in which we lose sight of the details, and it is very difficult for us to have access to the details to make efficient computation. Okay, what is the solution? Well, you know, templates are driven by concepts, okay? The problem that we have in C++ at the moment is that our concepts do not articulate concerns of performance or particulars of details of the execution platforms, okay? And that's a big problem. But there are very small examples, but examples nonetheless. For example, is trivially destructible. This is something that you can use to know that destroying that thing is a no operation. And this can drive lots of optimizations, okay? In particular, we implemented, by team, we make an implementation of variant, and then the variant always has to be destroyed. I attended yesterday the presentation by Alexandrescu that went over particularly that concern, because the destructor is always executed, right? Formally, even if it is an OOP, it has to be invoked. So making a variant trivially destructible when all of the alternatives are trivially destructible is a big performance gain, okay? And why we were able to do this? Because there is that one performance-sensitive descriptor trait that requires compiler magic, which is trivially destructible. Okay, now we can do more than that. There are type annotations, like for example in the guideline support library, not null, that all they do is to indicate, well, they do more, but their raison d'être is to indicate that the pointer won't be null, okay? And then you can leverage that in your code because you know that the pointer is not going to be null. So that's an annotation. You're saying something without changing the nature of what's in there. I have made an annotation that is called so-infrequent, and the later part we're going to show how you can use it. But this is important of constructing annotations, and we'll talk more about that if the time allows. Okay. What is our objective for the code to say more about the uses, about the performance considerations? We should start doing that tomorrow. Okay. People that work with data orientation, they have a different view of how to represent the state of things. And they frequently refer to the entity component system model, okay? And I'm just gonna read to you from the Wikipedia. This means that it's gonna have composition over inheritance, meaning that every entity is defined not by a type assigned to it, but by name sets of data called components that are associated to it. And the system is what maps the components to the entities, okay? So they have like a completely flexible and dynamic thing, which all those stuff there, the state of the entities are just data, and they are not collected into a type like in C++, but there is some system that says, yeah, you belong to that entity and you belong to that other entity and so on. Can this work in practice? We have taken two major features out of the language. We are not using encapsulation anymore, what I summarize as encapsulation, and we're not using inheritance and virtual. Well, yesterday, there was this good presentation by Eyal Sedaka. One of the great things of presenting on Friday is that you can make such a summary of the good presentation that has happened so far, right? So he said something that I absolutely loved. C++ is the language that provides tools to the programmers so that the programmers invent what was unimagined to the others. So we are getting away with rejecting two features of the language or our practice of how to do software, and attempt to use C++ features to accomplish something else, and probably we can get ahead. Like, for example, I'm just gonna say it, the type-erasure library that I have worked on for the last many years has better performance than inheritance and virtual, okay? It's better performance than the language feature itself. So that's quite remarkable. There are many people that have done in C++ things that the language supports natively, just with better performance or better in some other way. Okay. If we can do scattering and handles, we win, all right? There are many questions that I have left open, like exactly how you're gonna represent subtypes. But I want to just be wavy and say to you, we can do that. We haven't seen a real obstacle that would prevent us from doing it. Let's talk for a moment of what would be the consequences. We can use our caches at full efficiency. We could map memory to place the fields where they are going to be most useful to the executing engines. Because the data is homogeneous, we can use assembler magic for weird instructions more practically. There are considerations of auto-vectorization. You should go back to my presentation 2 years ago at CppCon for examples of how the compilers can do truly surprising things when the data is laid in a way which they like. Okay. I'm going to skip this. I have a coworker that is a great new coworker. He has worked improving Clang, and we were talking about polyhedral compilation, and this is relevant because changing the memory layout of the data might enable or not optimizations of that caliber. The name is Aditya Kumar. He presented yesterday, but let's keep going, okay? Now let's see, for example, let's see for a moment. I have here a Godbolt link. That the internet is disconnected. Cannot believe this. Yeah. The key to C++ is Stepanov, not only CppCon, not just CppCon. I'm just gonna skip, but this is not all. So what is the difference between addressing a field through the normal object or the handle? This is what I have here, okay? Now, you can see that using the handle is different, and you might be concerned whether it's going to be significantly less performing, but I'm gonna ask you just out of faith that yes, there is somewhat of a performance penalty here, but it truly is negligible, even cumulatively, okay? It's just a matter of, unfortunately, I don't think I have the time to explain to you why I say so, but I am firmly persuaded that it is. And this matches the benchmarks that the other people, because, you know, if you're not gonna do scattering to get the first version, the version on the top, that'll be, performance-wise, byte smart and cache line foolish, literally. Okay, there's an example of an API that is based on handle types. That's why I am extraordinarily confident that handle types are the way to go, which is the Unix API for I/O. You have something called file descriptors that don't describe anything and do not necessarily are files. So that misnomer, I think that what they are just handles, okay? OpenGL is another example. So the point to make here is that you always use the file descriptors through the proper API, and guess what? That is recovering the benefits of encapsulation. All right. Another thing that using handles prevent is that there is a lot of bad practice communication in our systems in which one object changes the state of another object, and that communication through mutation is just a spaghetti. It is unaccountable, and it just leads to problems, right? So using handle types is a disincentive to do those things. They make the debugging harder. You'll have to do some textual replacement, because when you invoke a function, you'll have to do the equivalent of invoking the handler instead. So you'll have to do that substitution somehow. I haven't found any way to help with that. Okay, how to do the scattering or columnar representation of the handles, okay? We need to respect for our users that want their code to continue to be more or less the same, to have the very same names, okay? The names for the functions should be the same, probably also the names for the fields, although we are gonna ask them to use accessors, functions that access the field, so that is not too much to ask. But we have a problem that we had to have identifiers. And if we have identifiers, then we need introspection, but C++ doesn't have it, so we are left only with bad choices. We had to pick our poison. However, there has got to be a way to specify our types so that these transformations of the scattering or the columnar representation can be done automatically. The solution that I have found for that is to use macros, okay? And if you want that the result would be something like this sprite made up structure here, this would be the way in which you would describe it using macros. Let's see if we can open that gist in here. So in this gist, I took a lot of effort to explain the dark art of using boost preprocessing sequence macros, and I hope it might be of value for the interested member of the audience. Now, let's go back to type annotations. And by the way, I think that we're just going to be able to finish in time, and maybe even a couple of questions afterward. Type annotations. So I want to talk to you about a made-up type annotation called infrequent. What is infrequent? Something that says that the optionality of the type that it wraps is going to exist very, very seldom. Like almost never is going to be present, okay? Optional, in which the vast majority of the cases won't be there. Understood? So that's the meaning of infrequent, what I am browsing through my cursor. And I need a little bit of metaprogramming, which is, I call it a recognizer, to be able to detect through the mechanism of partial specialization of templates that something is an infrequent, and see if I use a recognizer and it is not something specialized, then oh, darn it, I made a mistake here. Pretend that here it says a storage of T. And if it is a pattern that it recognizes, like for example, infrequent, then it's not going to do storage of T, but it's going to do an efficient map of whatever that recognizer would recognize, because you can have several decorations, right? So you have to recognize them all, so this would be to do it. It is metaprogramming. By the way, 2016 in my presentation at CppCon, I did far more complicated metaprogramming. So the point that I'm trying to convey to you is that this is absolutely possible, and only possible thanks to genetic programming, which is the point of the presentation. Okay, so I am working with a teammate. The name is Alexander Bacherikov. He introduced what we're working on. Well, this is work that he has been doing for longer, but I got very inspired about his work, and now I'm joining and trying to take it in the directions that I think are important. The presentation was STL algorithms as expressions, and to achieve the expression style, we are devising type annotations and other resources with metaprogramming that is going to improve the expressibility of these things. So that is the type of resources that we need to be able to tell in the source code that, in general, considerations of performance. Less general improvements. You can represent Boolean fields as bit fields. You can represent the small types as swards, and then you can go back to my presentation 2 years ago about swards and how much more performance you can get from doing that. The final part of the presentation is that if you're going to do serialization, okay, you typically implement it as subclassing. Then you have the problem of indirection, and this is utterly unperforming. Now, serialization in general involves tree traversals, pointer chasing. Deserializing is much worse because it's going to be doing small allocations all the time. So, if you have the equivalent state represented with scattering and arrays and stuff like that, you can probably get away with just taking a snapshot of the memory and persist it. And for example, a video game, you have literally millions of objects, or our idea of objects, and if you persisted them as a memory dump, then you don't even have to read the file back to do the equivalent of a save game load. You just memory map it. And the operating system is going to take care of actually reading from storage when the data is actually used. So I am literally working on that. I want to achieve it. The people that do databases have worked with this. Handles prevent you have negative incentives to do optional semantics or a state mutation that I think they are pestilences. Now, the conclusion is C++ features that data orientation people are hostile to, like operator overloads, template specializations, actually can help go from orthodox C++ into more data-oriented architectures for our software, okay? And sure, I have left many questions open, but I have not seen obstacles that will make me, ultimately I'm going to fail. No, what I have seen is quite the opposite. All I have is an overwhelming amount of choices on how to do it that are really compelling. It's just that I have to commit to some of them and do the work to put everything together. And so in that regard, I think that data orientation can be made practical through generic programming. Thank you very much. Well, until I get kicked out, I'm very happy to answer questions from you. Maybe they're not going to show up in the YouTube video, but I don't particularly care.
One challenge with this kind of modeling and multi-threaded programming is that you sometimes are trying to mutate data that other threads trying to read. Have you considered the idea that you could use copy and write from memmap of the operating system to kind of version?
The answer is no. The question was, this representation on columnar way sometimes may present obstacles when you're doing multi-threading. And the question was whether I have considered to use the equivalent of memory mapping so that we achieve something equivalent to a copy on write, so that each thread has its own. No, you have just made me aware of that possibility, and I think it is fantastic. I don't see any reason for why this will not work. And the operating system is going to take care of doing the copy for you. Fantastic. Uh-huh. Thank you for the question. It is whether the compilers can help substantially with accomplishing the data orientation benefits that we're talking about. I don't know. I wish my coworker Aditya Kumar would be with us at the conference live, because I could have directed the question to him, but we're still under COVID-19, so we'll have to take a rain check on that. My friend, my coworker, is formerly a compiler worker. He worked doing compilers, I think Clang, LLVM. We talked about the polyhedral computation in which, like for example, if you want to do matrix multiplication, okay, the compiler might see the two-dimensional space of the matrices and come up with an optimal plan. They're telling me that it's over. An optimal plan to execute the multiplication. However, this is very brittle. You need to be able to feed the data in exactly the easiest layout that the compiler would be able to use to accomplish these optimizations. Yes, so, okay. I think that we can have more questions, but I'm sure that I need to go. Thank you very much, guys.